For our last example, we're going to look at the Dirichlet function. Dirichlet was a 19th century German mathematician. He actually, I think, is given credit for defining what a function is. But he's given credit for this Dirichlet function, which is defined as follows. Capital D of x, D for Dirichlet, is 1 if x is a rational number, and it's 0 if x is an irrational number. So another way of saying this would be that x is an element of the real numbers minus the rationals, so the irrationals. Does the limit of d of x exist as x goes to 0? I think you could probably guess that the answer is no. As x approaches 0 from either side, we can make an interval around 0 that's going to have both rational numbers and irrational numbers in it. So that's going to cause this to fail. So no, it doesn't. Recall, the limit of f of x as x goes to a is not equal to the real number L. That means that for every epsilon greater than 0, there exists an epsilon greater than 0 such that for all positive numbers delta, this is true. X being very close to a, within delta of a but not equal to a, and f of x minus L is greater than or equal to epsilon. And that's what we'll show. So to show this, and this means this limit does not equal L for any real number. L is chosen arbitrarily. We'll let epsilon equal 1/2. That tells us, we know this, for every delta greater than 0, there is a rational number little q and an irrational number little t, that they're both in this interval. That's like saying that 0 is less than q minus 0 or t minus 0. And I could leave those out if I wanted to. I could leave out the minus zeros. And that's simply because that's all this means here. This means this. That's true because the rational numbers are dense on the real line and the irrational numbers are also dense on the real line. Every interval contains an infinite number of irrationals and irrationals. But d of the rational number q is equal to 1, and d of t, the irrational number, is equal to 0. Which implies that d of q minus L in absolute values, which is equal to 1 minus L, the distance between L and 1, is greater than or equal to 1/2, or the other one is. And that's equal to L minus 0 is greater than or equal to 1/2. And the limit does not exist. That's a little trick that we used a little bit earlier. But this time I had to use epsilon equals 1/2 or something smaller than that, because any number L, no matter where I put L on the y-axis, its distance at least 1/2 away from one of those two numbers. That's why I chose epsilon equal to 1/2. Or again, anything between 0 and 1/2 would have worked as well.